Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Interplanetary Climate Change, Planet X and the Current Grand Solar Maximum. Now, at a time when many people are talking about the sun going into a declining phase of activity or a grand solar minimum, the evidence shows that the sun has been doing the exact opposite. The sun has been on an increasing trend of solar activity since about 1850. And we can see that in this figure here. And this shows sunspot number versus years, and this line here, this gray line, shows directly sunspot numbers. It's a 10-year average number, and then the other lines, like the gray line with the vertical lines across it, and the black line, come from ice core sample data. But all of these seem to indicate that the sun has increased in solar activity. And we can see how it has increased since about 1850. This is about 1850 there. It has increased and gotten to an all-time high. And it is higher than anything else we have seen in 1,200 years, as we can see from these curves here. So this goes back to 880, and later we'll see some more that shows that it's even more meaningful than that, that if we go back even further, then we also see that we are at an all-time high of solar activity. Now, this actually agrees with the evidence that indicates that the Planet X system of stellar cores started entering the solar system in about 1850, and that it was the arrival of stellar core dust in the solar system and its entrance into the Earth's atmosphere which led to the appearance of noctilucent clouds. And these clouds were first observed in 1850. For more details on that, you may look at Article 275 entitled Planet X Debris Field Impacting Earth. And here is another diagram also with sunspot numbers. And so that's the black line with the stars is sunspot numbers. The green and the purple are from ice core sample data as well. The solid black line is actually cosmic ray measurements coming from neutron monitors since 1951 and ionization chambers since 1936. And we can see that the cosmic number data seems to indicate that cosmic rays go up when solar activity goes up. And this is contrary to what is believed. So notice that cosmic rays go up with solar activity. This actually suggests that the sun is the source of those cosmic rays, because this is contrary to the popular belief that when solar activity declines, as indicated by sunspot numbers, then more cosmic rays manage to enter into the solar system from outside it, thus leading to increases in cosmic rays. However, as we saw, the data shows the opposite is occurring, and thus indicates that the sun is the real source of cosmic rays impacting the Earth. And here's another sunspot versus years chart. This one goes back to minus 9,500 years AD or 9,500 years BC, or actually 11,500 years from now. So here we are at 2,000 years. That's where we are now. And we can see that the solar activity, according to sunspot number, is at an all-time high, at least if we look back, well, it's higher than anything we've seen in the past 6,000 years. So over here we are at 6,000 years from now. That's minus 4,000 BC. And any red would indicate anything above normal solar activity. So a grand solar maximum if we have a red appearing, because then it would be above this red line. And any blue indicates a grand solar minimum. So we see that several instances when that occurred, but this indicates an all-time high of solar activity right now around the year 2000. And if we go back, as I said, to 6,000 years ago, we don't get anything as high as that. And if we keep going back here, we see some grand solar maximums here, but not as high as what we have right now. And if we go back even further, we have to go back to about minus 9,000 AD to get solar activity that's higher than what we have here at around the year 2000. So this means that the sun is actually at a grand solar maximum, a grand maximum of solar activity. And we can see several solar grand minimums here. For instance, this one here, we see there was one here between 1,000 and 2,000 years. And after that we got this solar maximum. So some people might say, looking at that this might be a rebound effect of the sun. However, we had grand solar minimums here and no grand solar maximums following it, or before it or after it. So I don't think this data shows that there can be a rebound effect from the sun. This seems to be something else that's causing the sun to have maximum solar activity. And because this is about 200 years from the year 2000, so about the time that the stellar cores, I believe, started entering the solar system, as indicated by the noctilucent clouds. And we can see that that's when this activity started increasing about there. There was a little kink in it, but then it basically went on going up. So we seem to be at a grand solar maximum. Now, in spite of all the data showing that solar activity has increased for the last 100 years or so to a level not seen since minus 9,000 AD, there is also data showing that the sun is weakening. The sun's magnetic field associated to sunspots declined all through cycle 23, showing a weakening of the sun through that cycle. In addition, the sun's light emission has clearly declined since 2011, and this can be clearly seen from SDO images in various wavelengths. So how is this possible? The truth is that the sun is both more active and weaker, and the stellar core system is causing both effects on the sun. Even though these effects may seem contradictory at first, they are not. As shown in Article 2, Interplanetary Climate Change, Planet X causes solar flares, the stellar cores provoke the sun into having solar flares and coronal mass ejections through their energy drawing ability once they are in the sun's corona. Since larger numbers of sunspots appear before a solar flare or CME event, it follows that the presence of stellar cores leads to increased numbers of sunspots, which are correctly interpreted as a sign of increased solar activity. However, the stellar cores have also caused the sun to become weaker, since the sunspots it is producing have a lower magnetic field associated with them. The sun is also emitting light of low intensity, indicating that its ability to emit light has decreased. In other words, the stellar cores, through their energy draining ability, have made the sun both more active and weaker. And here is the data from a study done by Livingston and Penn, which shows that the sun's magnetic field strength associated with sunspots dropped independent of the solar cycle during cycle 23. And they found that it consistently dropped by 50 Gauss per year between 1996 and 2009. The stellar cores draw energy from the sun, so it logically should become weaker. And since energy is associated to the sun's gravitational influence on other objects and on its own matter, and you may look at article 210 entitled Stellar Core Gravity, Tidal, and G is not constant, where this is explained further. As the stellar cores draw more energy, the sun will find it more difficult to hold on to its surface plasma, which should then make it easier for the stellar cores to provoke it into having solar flare events and CMEs. Hence, as the sun becomes weaker, it is also more likely to suddenly become extremely active if a new large stellar core arrives at the sun's corona. Thus, if there is a time span during which a new large stellar core does not arrive at the sun's corona, the sun may seem to have very low activity and thus have a period when very few sunspots appear, but it may then suddenly become very active. And this seems to have occurred in 2017. In March of 2017, for a period of 15 days between the 6th and the 21st of March, the sun had no sunspots at all. And however, in June, the sun had an X9.3 solar flare. At that time, the sun had not had a major solar flare since July of 2005, when it had an X17 solar flare. So this was the first major solar flare in 12 years. Because the sun had been showing signs of extremely low activity, this was very surprising. However, what must have occurred is that a new large stellar core must have arrived at the sun at around that time. As stellar cores once in the solar system do not seem to leave the solar system, they will continue to draw energy from the sun, and it will thus continue to weaken, and as it weakens, it will become more reactive to the appearance of a new large stellar core, and therefore more likely to have a large explosive solar flare after a period of seemingly having gone to sleep. And here are images from the SDO satellite in 304 angstrom showing the sun from 2011 to 2018 and how it has become so much darker, indicating that the light intensity is lower and therefore the number of photons emitted has decreased, and therefore showing that the sun is having trouble maintaining the same light emission. This means that the sun is weaker and emitting less light. And this is a LASCO C2 image of the sun from July 23rd, 2017. There was a large CME on that day, and there is a stellar core in this image. You can see it's a solid spherical object. This is perfectly spherical, and only a spherical object can maintain that shape, and it maintains its size in several frames. And the size, if we compare with the circle here, which indicates the size of the sun, is about the same size as the sun. So this is a large stellar core, and it's seen within CME materials. It moves away from the sun. It had to be very close to the sun. So this image, as I said, is from July 23rd. The major solar flare occurred on June 9th. So this may actually have been the stellar core that arrived at the sun around June 9th, 2017, and most likely led to that solar flare. And so this is most likely what happens. This is why solar flares occur. So in conclusion, the sun seems to have become more active than it has been in 11,000 years as a result of the Planet X system of stellar cores having invaded the solar system. Through the energy draining effect, they have made the sun weaker, leading to a lower light emission and a lower magnetic field associated to sunspots. And yet, as energy is associated to the gravitational field, this would also mean that the sun would become more reactive to the presence of stellar cores, and thus more likely to suddenly becoming extremely active after a period of low activity. That is when a new stellar core arrives at the sun's corona. And here are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.